Last week we looked at Pythagoras and how it can be used to detect whether or not points are inside a circle. So we had a review of what Pythagoras was, which is basically r to the power of 2 is equal to x to the power of 2 plus y to the power of 2. We also looked at what happened if you use different powers, which gives you different shapes. So we understand that in order to use or detect rather points inside a circle or points inside a particular shape, we can use the Pythagoras theorem. We also looked at what happens if you nest the if statements so that you can create much more interesting and much more complex shapes. So your algorithm can be much more complicated and it can be layered in its complexity by using if statements. We were plotting points, and points basically are positions. So we can understand that a position is made from two components, an x component and a y component in 2D space. So any point on a 2D screen needs both an x and a y. So a position is a point. A position is also a vector. The symbol for a vector is an arrow above the variable, as we can see here. So we can understand that what we have been doing last week is we've been dealing with vectors. And vectors are complex numbers. In other words, vectors are numbers that have several components. We've been dealing with two-dimensional vectors which have two components. So a point P is a vector. It's also a point, and it can also be defined as a vertex. And you'll come across vertices more often when we're dealing with 3D, because that's how we create meshes, by having points in space that are connected with faces, and that is how we draw 3D objects. So we now should understand reasonably clearly what a vector is. We also need to consider that a point and a vector are mathematically equivalent. In other words, from within the field of mathematics, we treat them as identical components, and they can be interchanged. That doesn't mean that they're actually interchangeable, because by the definition we use them in two distinct ways. So we use vectors in a particular way. For most of what we do, a vector is a direction in space with a magnitude, in other words, with a distance. Later on, we will look how homogeneous coordinates can distinguish between a vector and a position. And this will enable us to distinguish mathematically between a point and a vector. So we know that points are a place and vectors are considered to be a direction or a movement. If we have a quick look at this link, we can see that what we have here is we have our 2 points in space, and we have a vector that goes between them. So we have a vertical component, which we usually label the y component, and we have a horizontal component, which we usually label the x component. So you can see we have A and B. Point A to point B is a vector, and it is made up of 2 scalar values. The 7 is the x value and the 4 is the y value. So there is 7 units between A and B on the x, and there's 4 units between A and B on the y. And we can see how this is made up. A 7 units, B 4 units, and then we have a distance, the vector AB, So in the code, you have been adding and subtracting the y values, and you have probably understood that you need to do a set of instructions. The algorithm needs to act on both of those components inside the vector. So when you're adding two vectors together, you have to add both of the x values together and both of the y values together. When you're subtracting vectors, you have to subtract the x from the x and the y from the y of the relative vectors. And this is adding and subtracting vectors. This is how it is done. So to add or subtract two vectors, you have to add or subtract the like components. And this will scale up when we get into 3D. At the moment, we're just doing x and y. When we do 3D, we'll be doing x and y and z. The vectors will have 3 components, and we'll have to act on each of the 3 components. So that concludes our review of last week. So moving on to what we're doing this week is we're looking at how we can move from point A to point B. This is quite a common process in games. Seems very obvious and it appears very simple, but it isn't necessarily so. This application can be used many times, just moving objects around, when you're firing bullets, whenever there's a transition, when you even want to move things around on the user interface, you're usually moving things from one position to another position. So first of all, we want to define the problem because the definitions are important. We don't want any confusion about what we actually mean. Constant speed we're going to define as the distance per frame is the same distance. We're assuming that we're frame locked, which means that each frame takes the same amount of time. So we could be running at a steady 30 frames per second. And that means that the distance that we travel in each frame should be the same distance. We want a consistent speed, which means the distance per frame is the same for each node. Different shots at different targets should still travel at the same speed. We want it to be omnidirectional. In other words, it should work for every single direction. There should be no directions in which the speed changes, and there should be no directions in which the bullet cannot progress. It should travel in a straight line. There should be no change of direction during the movement. And it should be accurate. It should reach the target location. But again, we have to be careful about what the definition is of accurate, because accuracy is a vague term and you need to specify it. Often we use the definition of equal, and in computer programming, equal is a tricky subject. If you're not dealing with integers, you really can't be sure that things are actually equal. But first, let's discuss what is speed. We have 3 components. We have distance, speed, and time. We know that distance is the speed multiplied by the time. We know time is the distance divided by the speed. And we know that speed is the distance divided by the time. In other words, we know this from the fact that speed is actually even described in this way. So when we talk about distance traveled, we talk about the distance per unit of time. So we have miles per hour, and we have kilometers per hour, and we have meters per second. And what that means is it is the distance divided by the unit of time. Our first example will be using a simple increment. So we have a function here which basically looks at the 2 values that we've got. So we have a current x value, and we have a target x value, we have a current y value, and a target y value. So the current value is trying to get to the target value. If it's less than the target value, we increment x, and if it's greater than the target value, we decrement x. Obviously, if they're equal, we don't adjust the current value. We do the same thing for y, and then we're just going to draw our target position, and we're just going to do a little test to make sure if we've reached the target, and if we have, we're going to stop it trying to get towards the target. Let's just run this. So when we click somewhere, you can see that it looks pretty good to start with. It goes off, but then it reaches a point and it veers off to one side. And if we try different positions on the screen, you can see that we get different results. And most of the time we're getting a little bend at some point in our progress. And that is because we can only increment by 1, which means that sometimes we're doing x plus 1 and y plus 1, and sometimes we're just incrementing x, and sometimes we're just incrementing y. So we're not really getting a rate of change. So this is the problem with the first version that we've got. So okay, we understand that this doesn't work very well. It is accurate, it does reach the destination point, but it's not a straight line. So rather than just incrementing the x and the y by 1, what we really want to do is we need to add a different amount to x and y depending on how big the x and y values are. So let's look at this. What we're going to do is, where did I get to? Right. What we're going to do is we're going to calculate a delta. In other words, we're going to take our x and our y values. We're going to look at a proportion of that. We're going to take, say, 1% of the overall x distance and 1% of the overall y distance. We're going to recalculate that every tick, and we're going to see where that gets us. So now if I click, you can see we start off very rapidly, but we soon slow down. And the reason that we're slowing down is because we're calculating the distance every single frame. We're taking a percentage of that, and then we're moving that distance. So the next time we do it, the distance that we're checking is smaller, which means the distance we move is smaller. And what this effect means is that as we get closer and closer to an object, the movement gets smaller and smaller, and so we effectively slow down and never quite reach the target. So even for very small values, you can see it moves slowly and doesn't get there. When I click on a big distance, you can see jumps very quickly at the beginning. This system can be quite useful for camera control when you want the camera to slowly move at the end into close of where the camera should be. So if you want the camera to track quickly into a position, but not stop quickly in a jarring motion, then this is what we call an ease in, because we're easing in to this position. Useful, but in this case it's not what we want. So, and the problem for this is because we calculate the delta every tick. So first of all, it's more efficient just to calculate the delta once at the beginning when we set when we have the mouse click and we want to set our variables up. But also it's very important, if we want that delta to be consistent, we shouldn't be changing it. So now that we've changed that, let's go and have a look at see what happens. So you can see that now our rate of change, in other words our speed, is a constant speed So wherever I click, the speed of this particular projectile is constant, but it's not hitting the target. You can see if I get close to, say, a vertical axis, you can see that it's just going straight up. It's just not quite getting towards the target. And the reason for this is because we're using integers. If we add a small amount, say 0.1, to an integer can only hold natural numbers, which are whole numbers. So an integer can't hold 1.1. And if we add 0.1 to 1 as an integer, it doesn't jump up to 2. What happens with most integer values is that they round down, or they will round at some point. There has to be a rounding error. So what's happening here is we're getting a rounding error because we're using integers. So let's not use integers. Let's use floating point. Right. Okay, now when we shoot at the target, I managed to get one there where it did reach. I don't think I'm going to get that again in a hurry. Oh, I did. And I clicked away. There we go. Okay, so this looks much better. In fact, if we try and do some angles that are very close to the y or x axis, you can see the trajectory is good. But what's happening is that it's going straight through the point. And most of the time, it doesn't recognize a hit. And in this case, it does recognize a hit. So we have to work out why is it only sometimes recognizing that it's reached the target. And if we look at the output that is being printed in the debug log, you can see that our target position is 506. And you can see that our value got from 495 to 506.000061. Very close to 506, but not exactly 506. And this is an important thing. If you're comparing integers and floats, you're going to have problems because your floating point values have a level of precision, and it's very difficult to be sure that they equal a whole or natural number. So how are we going to fix this? So if we have a look at how we stop in this function and how we stop in the fixed version. So our test here is if the current x is equal to the target x and the current y is equal to the target y, then we call the stop function, or we set the stop flag rather. Our problem is that our current x is a floating point value and our target x is an integer value, and they are probably never going to equal out. And this is also true for integers. If you compare two integer values that have been equated with different mathematics, there can be problems where they don't equal what you expect them to equal, and therefore there is a rounding error. The way I fix this is, instead of comparing current x with current y, current x with the target x, what I've done is I've subtracted one from the other, and then I've calculated an absolute value. This will give me the distance or the change between the two. Then what I've done is I've taken the absolute value of the dx, which is our rate of change, and providing that this the distance between these 2 points is smaller than the rate of change, then we know we've got as close as we can using this particular rate of change, and therefore we can set the flag. So let's see if that works. That looks pretty good. So, is this right? Is this doing every single thing that we want it to do? Well, one of the key points is that it should be a constant speed, which we're certainly doing, but it should also be a consistent speed between each mouse click. And you can see that the further that I click away, the faster the bullet is traveling. And if I click very close, you can see that the bullet is traveling slowly. You can tell this by the gap between each plot. So this is where the interesting stuff comes in, because we need to find a way of what we call normalizing this value, or in this case we need to create a unity vector that we can use to multiply by the speed. So we've calculated a rate of change, we've looked at the effects of integers and floats, and we've looked at some of the problems. We know that the compound number, the complex number, that should read. I'm going to fix that now. We know that the complex number xy is known as a vector. We know that it's a 2D vector. What we should be looking at is to make a unifying, we should be unifying the rate of change, which means we need to make sure that we have a unit vector. We are going to make our vector the length of 1, because the length of 1 is very useful. 1 times 1 is 1, 1 divided by 1 is 1, 1 to the power of 1 is 1, x to the power of 0 is 1, and x to the power of 1 is x. Most importantly for us, speed times 1 is speed. So if we multiply our vector, which is a unit length, by the speed, we will have a vector that is the right velocity. And a unit vector is basically all of the vectors that plot out a circle that has a radius 1. All of those vectors have a length of 1, and that is a unit vector. So we need to know how you derive the normal vector or the unity vector from any vector. Let's have a quick look at the steps for the length of a line segment. So we have two segments here. Step 1, we locate point C below B and right of A. Then we calculate the length of A and C. We calculate the length of B and C. And then we calculate the length of A and B, which we know is Pythagoras. And that gives us this length. So we can calculate this length. This is what we were doing before when we were trying to hit inside a circle. We've got a 3-4 triangle here. Our y value is 3 and our x value is 4. So what I want to do is I want to work out what this value here, and this is, I'm going to call this magnitude. I don't have a pen, so I'm trying to write everything with the mouse, which is weird. Okay, so 3 squared is 9, and 4 squared is 16. 9 and 16 is 25. So we need to calculate the square root of 25 to give us this magnitude, because mag squared equals x squared plus y squared. Yeah, now I wish I'd plugged in my tablet. Okay, so, and the square root of 25 is equal to 5. Okay, that's good. So what I need to do now is, now that I know that this is 5 long, what I need to do is I need to divide this length by 5 and this length by 5. And this will make these lengths shrink in proportion, because what I want to do is I want to shrink this down until this is just the value of 1. At the moment it's at the value of 5, and obviously if I divide 5 by 5 I get 1. So the same too for the components of this complex number. So 3 divided by 5 is 0.6, and 4 divided by 5 is 0.8. And this is our y value, and this is our x value. This looks, or it can look a little strange. Why aren't these values 1, or at least why don't they add up to 1? And they do add up to 1 if we do the Pythagoras equation. So let's do that and see what happens. So this value here is 0.6, and this value here is 0.8. 0.6 squared is 0.36, and 0.8 squared is 0.64, and if we add 0.64, 0.36, really bad writing here. 6 and 4 is 1. 6 and 4 is 1. So we end up with a value of 1. So we've proved that these values, 0.6 and 0.8, add up to the unit vector. I recommend that you do this with some other values so that you understand how you normalize a vector and how you normalize the components within that vector, so that you're familiar with how these numbers should come out. These numbers should never come out more than 1 for obvious reasons, otherwise this length is bound to be longer than 1. We know in theory now how to calculate the unit vector. So let's have a look at the problem that we have for this week. This is the rock, and you can see it's moving slowly through space. If it goes off the screen, it will respawn. It doesn't do anything if it hits the ship, because we're really worried about that. What we're trying to do at the moment is we're trying to get this bullet working. It's traveling anywhere on the screen, and it travels at a constant speed. It also is able to hit the target. Note that the bullet isn't destroyed. It just goes straight through this rock, and sometimes on and destroys another rock, but that's okay. This is where I want you to get to in the laboratory sessions this week. And if you get this working, what I want you to do is I want you to make the bullet radius a lot bigger. So let's set this to 25. And what I want to happen is I want the bullet to destroy the asteroid the moment it touches. You can probably see at the moment, and I will slow it down so we will look at our speed. Might make it harder to shoot. So you can see, haha, the bullet's not going to catch the rock. Let's try. You can see how the bullet and the rock overlap. I don't want that overlap. I want the rock to be destroyed the moment the bullet touches. This will be a good one. This will be good. See that overlap? Don't want that. I want the bullet to destroy the asteroid the moment it touches. So I want you to figure out that. You know how to figure out whether a point is inside a circle. So I want you to kind of rack your brains and figure out how you can work out whether two circles are touching. And if you don't meet the stretch goal, we will be explaining it next week.